In this video, we're going to discuss subcritical fracture propagation. This is a topic which is not widely known, but is quite important in order to understand not only hydraulic fracture propagation and fluid-driven fracture propagation, but also natural fractures in rock formations, how they form, what is the spacing, and uh, what are the factors that control that. All right, so in this topic, uh, what we're going to do is we're going to first explore the velocity of propagation of a fracture in mode 1. So for a minute, let's not consider the fluid within the fracture, but just let's consider a mechanical problem in which we have stresses which are applied. In a rock, there is a flow in the middle, and as a result of these stresses, if the stresses are large enough, a fracture might start propagating from the tips. And this is going to be an open mode fracture for this particular case. Well, it turns out that the velocity at which this fracture propagates is a function of the stress intensity factor, Ki, so that the logarithm of the velocity usually shows a signature that go more or less as the drawing that you see over here, divided in three regions. First, there is a region in which the logarithm of velocity is proportional to the stress intensity factor. Then there is another region in which there is not much of an increase anymore, but then in a region 3, that velocity increases significantly. So this is the region in which we have what is called subcritical fracture propagation. And let me fix that. And in this regime, the velocity of the fracture is going to be proportional to the stress intensity. So the limit here is going to be this parameter Ki star, such that if I don't have enough stress intensity, a fracture will not propagate. But as soon as I reach a value which is equal or larger than that, a fracture will start propagating, but at a small velocity. And here we're talking about very small velocities, probably in the order of a centimeter per day or less. We're going to see some numbers later on. So in this region of proportionality, then is when we have this phenomenon of subcritical fracture propagation. And the maximum value possible is going to be the fracture toughness, KIC. And that's why we call it a critical value of the stress intensity factor, because that's the value at which a fracture will propagate at a very large velocity. And we can capture this region 1 of this response through this equation over here, in which the velocity is equal to proportionality factor A times the dimensionless stress intensity factor Ki divided Kic times n, where n is what is known as the subcritical index. So we can do a little bit of math in this case, and we'll see that if we apply a logarithm to both sides, what we end up with is with this equation in which the logarithm of velocity is proportional to the subcritical index times the logarithm of the dimensionless stress intensity factor. So the main parameters here that are going to affect this response are let me do it with another color, the subcritical index factor, also sometimes goes by SCI, and also the fracture toughness, something that we already knew from previous examples and videos. All right, this particular equation is going to apply to an open mode fracture or mode 1. Similarly, you could have similar equations, and of course the proportionality values are going to be different, the toughness is going to be different, but you could also have these cases for mode 2 in which you would have a fracture that will grow in this direction, not in the plane of the original flow, because this one is caused by shear, and also you could have the extension to mode 3. Mode 3 is a little bit more difficult to draw into dimensions, so I'll just leave it like that. But you may want to check previous videos about what mode 3 is, and the same thing, the same logic is going to apply for mode 2 and mode 3 as the one that we're discussing right now for mode 1. All right, so now that we see this proportionality, let me share with you the figure of a paper that shows an example of these figures. So let me fit this into the window, and not that one. Okay, so this window, here we see a plot of the logarithm of the velocity of the fracture as a function of the dimensionless stress intensity factor. Notice that this is a logarithmic scale too. And what you can see is the relationship of the velocity with the, as I said before, the dimensionless stress intensity now for different materials and with different subcritical indices. So the smaller the subindex, then the flatter this curve is going to be, and the lower the increase of velocity is going to be with increase of the stress intensity. And different materials are going to have different responses, and of course different toughness, but also different subcritical index factors. All right, so let's see why this is important. What do we do with this? All right, so here I have another paper to share with you, and this is something that I'm going to post the links in the video. Here we have a paper. Let me go and share the title with you. By the way, the first one is this paper, and the second one is a paper that discusses the influence of subcritical fracture propagation on patterns of natural fractures in situ. And let me scroll down. Basically, in nature, several times we observe sets of fracture with a given spacing, and predicting that spacing and getting to know what is that spacing in subsurface condition is quite important, and is related to this subcritical fracture propagation. And here we see one more picture with fracture sets. And in this paper, what Professor Olson does is to run simulations with this plot we have just seen, and the equation we have just seen also, run simulations with different subcritical indices like n equal to 5, n equal to 20, and n equal to 80 in order to explain what would be the expected fracture patterns of these places where what you can see, these is small dashes, those are rock defects, and when this mass rock is subjected to stresses, then the fractures start to propagate. Basically here we have pulling in direction y, so that you have open mode fractures that propagate in direction x. And the subcritical index is going to play a role here in what are the patterns for fractures. For example, we can see in this case that the smaller the subcritical index, the more closely spaced these fractures are going to be. If the subcritical fracture index increases, then you start to see more separation between the fracture sets and something which looks closer to what is called a fracture swarm, with several fractures which are close to each other. If you want to try to understand why this is happening, remember that here a critical factor is the subcritical index, in which the higher the subcritical index, then the higher is going to be the velocity of propagation with increasing intensity. What means is that with small increases of intensity, some of these fractures are going to propagate very quickly. And what that's going to do is going to favor the propagation of fractures in specific areas. All right. So I don't want to draw general conclusions about these figures right now, because this is also a function of the stresses applied and also on the boundary conditions. For example, if you go further in reading this paper, you will see that different fracture patterns also are possible with the same subcritical index and with the same amount of initial flaws, depending on, in this case, the bed thickness. And that means basically the boundary conditions in this particular example. But the main message here is that subcritical index is going to be something that is going to play a role, is a factor that is going to play a role not only in this natural fracture spacing and explaining natural fracture formations, but also in the propagation of fractures when you do hydraulic fracturing. So let's see that approximation or that prediction for hydraulic fractures. And here we see another paper from Professor Olson. Let me move to the top, show you what the title is. And in this paper, what we see are also numerical simulations that explain the patterns of joints in naturally fractured rock and also applications for hydraulic fracturing. So let me go ahead directly to the hydraulic fracturing case. Without flaws, we see similar response to what we have seen before, that the closer the spacing between the clusters, the more interaction is going to be between the fractures. I recommend that you see the previous video if you haven't seen that yet, in order to get to know what's going on here. But here the interesting thing for this particular video is going to be what is going to be the effect if you have initial flaws or discontinuities in a rock mass. And all rock masses have some discontinuities, some flaws. All rock masses, natural rock masses, are heterogeneous. There is no such thing as a isotropic rock and a homogeneous rock. So in this case, the simulation considers the initial flaws and what will be the effect of fractures that propagate with these initial flaws, and what also are the effects of the initial flaws on the fractures. And here you have two cases. You have a case in which there is relatively small differential stress in the horizontal direction. So here we're looking at the top view in a case with normal faulting. So we are just interested in the stress difference between the maximum horizontal stress and the minimum horizontal stress. And what we can see is that if there is a small differential stress and if you have initial flaws, subcritical fracture propagation can also play a role in determining the geometry of these fractures. And for example, what we can see here is that there is fracture interference and interaction from different clusters, but also very important, and highlighted by this box over here, that because of the presence of the fractures, we see that adjacent to those fractures, we can also have propagation of shear fractures because of the high stress intensity at the tip of some of these fractures that induce propagation of other fractures which are not the main hydraulic fracture, and eventually if they join, they might join into a larger fracture. And the second case, it's a case with a higher differential stress. So in case of a higher differential stress, then there is not that much of a fracture bending. There is still quite a bit of interaction with the initial flaws, but it's less than the case before. But the main message here is that subcritical fracture propagation can also affect the geometry of hydraulic fractures in hydraulic fracture treatments. All right, so how do we measure this subcritical fracture index? We haven't seen any test so far that will help us to do that. And this is done with what is called a double torsion test. And here there is another paper that I also recommend, and I'm also going to post a link in the video that you may want to check, that covers a little bit of the fundamentals of subcritical fracture propagation and also the test required to measure that subcritical index. So basically what we have here is a rock slab in which a force is applied on two rollers, and you have here the reaction from two other rollers, such that when you apply the force in this location, you're going to generate a high stress intensity at a pre-made tip, so that the fracture is going to start to propagate here in the middle. So actually from this groove, and it's going to propagate along this direction, and the velocity at which it propagates is going to depend on the subcritical index. So you can see a few more details about this test in this paper, and similar equations to what we have seen before. What I like to highlight in order to finish this video is here an example of those velocities. So you can see that the velocity of fracture propagation can be quite small in the terms of 1 micron per second to 1 millimeter per second. And this is not only going to depend on the rock, but also very importantly is going to depend on the medium in which the rock is subjected to. Actually, this phenomenon of subcritical fracture propagation is related to chemical interaction of the rock with mechanics. It's a chemomechanical coupled process, and this is also a topic which is relevant to other applications in mechanics, in which you have corrosion. And this subcritical fracture propagation is partially driven for that effect by corrosion at the tip, or degradation of the properties at the tip of the fracture. So that if you have different fluids, the response is going to be different. The subcritical index is going to be different, and also the toughness could be different depending on in which medium you have the rock. And what we see in this example is that if you were to have a dry environment, non-corrosive environment like nitrogen, the toughness of the rock is going to be higher, and the subcritical index appears to be also a little bit less, and we will have this region 2 a little bit more well defined. As you increasing corrosiveness of the medium, going to ambient conditions in which you may have other gases, like for example CO2, and going into water, the toughness is going to be reduced, and also the subcritical index is going to change. So the subcritical index then is not going to be only a function of the rock type, but also of the medium in which the rock is in, or basically the pore fluid. You could imagine also you could run some of these tests in an acidic solution, and the response is going to be quite different too. All right, so I encourage you to read this series of papers. Again, I'm going to post the links. Subcritical fracture propagation recently has helped us to understand better the geometry, actual geometry of hydraulic fracture treatments, and also the presence and the geometry and morphology of natural fractures in naturally fractured formations.